Today, we're going to talk about ring strain. Now, you might remember that carbon likes to form the classic Egyptian pyramid shape for the faces. Now, let's put some background in for that 3D projection. Oh yeah, that looks good. I like that. Okay, so we'll put the carbon in the middle here. It's kind of hovering in space, and it likes to connect to these corners with its bonds this way. So what you see is this kind of three-dimensional thing. I'm trying to draw it in perspective here. It's not bad. Let's see if I can do a little better job. Maybe this will be my longer one. I'll have that in the back like that. I think you get what I'm trying to draw here. So this angle is not 90 degrees. If carbon was flat, its four bonds would be 90 degrees and it would bond to things like that. But it's not. This is 3D space. It's more than 90 degrees. In fact, I can calculate the vector if you're ever interested, but this angle here is about 109.5 degrees. That's where carbon is happiest because all of these bonds are the most apart. You'll find this angle distance is 109, this angle distance is 109, this angle distance is 109. It's just a matter of how you're viewing it in space. You know, we're just trying to draw 3D on a 2D surface here. But I assure you, this is the correct angle. So sometimes molecules are bonded in an unideal way. I'll give you an example here. Let's keep that 109.5 out. Well, I don't think we need it. Let's get rid of all of that. I gotta get rid of that little tiny piece there. It'll make me nuts. Okay, so let's take a look at some things that aren't, some things that are obviously not. How about what we talked about in the last video? Here's cyclopropane, 3 carbons. Prop meaning 3, right? Cyclo. Propane. And cyclopropane accessories. Now this is going to be an equilateral triangle. So you know that the angle here is only 60 degrees. But this carbon, it wants to be like another 49 degrees or whatever that it doesn't have. So look how extreme that is. And you could think of this just like trying to bend something on a spring. You're adding energy into the situation. It wants to break apart so bad because it wants this 109.5 degrees and you're kind of folding it in against its will here. Now this is bonded, so it's strong enough, but not as strong as if something was bonded like cyclohexane, which has just 109.5 degrees. It's got perfect alignment with what carbon wants. Perfect alignment. There's no ring strain in cyclohexane, which is why things like benzene rings are so common. Like you're going to see so many hexagons in organic chemistry with double bonds every other like this. There's no ring strain. It's so comfortable. It's a low energy configuration. Cyclopropane requires effort. You have to get some kind of mad scientist to come in and put some pressure on the situation to fold these together like this and hold them together against their will. It's almost wanting to pop at any moment. Cyclopropane is not very stable. As a consequence. What about cyclobutane? Well, here's 90 degrees, and it wants to be 109.5, right? So you're off by 19.5 degrees. Now that's not as bad as 40-something degrees from cyclopropane, but this is still strained. This is what ring strain is this angle, let's call it the unnatural angle, or a higher energy angle than the natural angle of carbon's existence. This is not what it wants. So if I'm to make a graph, in fact, I think I can just bring it in at this point. If I want to make a graph of ring strain for different carbon configurations, let's bring this graph in here. Yes, I prepared it. I came prepared today. Check this out. Look how much energy cyclopropane's ring has here. This is crazy. And butane is right there with it, actually. You wouldn't think so because the angle isn't nearly as extreme, but it is. And then pentane, way less. Hexane, notice none. There's none here. This yellow's not very good for writing on top of it. 6 here is the magic number. And then as I'm adding to the rings, look, you're getting ring strain again because they're not forming the ideal angle until you hit 14. So these are some magic numbers that show us like how comfortable your carbon is in its environment. And when you have cycloatoms, it's important, or cyclomolecules, it's important to be able to look at this and say, yeah, like, okay, cyclobutane can exist. I can create it. You can create almost any molecule for a moment, but how stable is it? How comfortable is carbon like that? What's its desire to break apart? And as a consequence, what's its willingness to react with something else? Because if you take cyclopropane and just add a little bit of heat, it's going to say, to hell with it, I'm already overwhelmed. The heat is too much. I can't hold my bond. I'm already under so much strain. This bond just isn't going to keep. It's going to break a lot more easily than something like what you see in cyclohexane. And that's really important to keep in mind as we're going forward with ring strain, because different parts of molecules, let's say I draw a hexane like this, and then I give you a cyclobutane out here and a cyclopropane out here. You don't know what's going to be drawn. You don't know. These show up in things, especially in explosives. Well, you're going to want to be able to look at this and say, there's ring strain here. This is the part that's going to want to react first. Like this thing wants to explode out of there. These bonds are not comfortable like this compared to here. This bond is way comfortable. It's neutral. It's not like being dipole pulled by anything positive, negative. Everything here is neutral. But the ring strain on cyclopropane and then cyclobutane are going to be the things that do the reacting before you're going to get anything out of something comfortable like a nice stable cyclohexane. So just keep that in mind as we're going forward. Pretty easy to have a look and be able to understand this once you know that the natural angle is this 109.5. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.